Okay, so Anurag, why is this not showing just my Blackboard? Okay, let's test it. Okay. Okay. Are we live? Okay. 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 So hello and welcome. I'm Prasad Subramanian. You've seen me on the lectures, so I'm live here. Happy to answer your questions, whatever you might have. I am also ready with some example problems that we can solve. A few representative problems that I feel. I mean, given the kinds of questions that have been asked on the forum, I have a couple of problems. That might be useful. But if you have any specific questions, please ask them on the chat box. Yes. All right. Hello, Karthik. Yes. So you have a specific question? Please ask any questions you might have. Maybe, okay. Right. So maybe what I should do instead is start out with a problem. Okay. Okay. I see there is some kind of a lag on the YouTube channel. Okay. No, I think it's okay. Right. So what I thought I would start with, there were several questions about there were some questions okay. So yes, Yash, I'll answer your question in a minute. Okay. Rotational and irrotational flows. So I will work out a problem right now. Okay. Now, Yash, of course, you need. It's good to have books. No, absolutely not. The video lectures are definitely not enough. And if you look at the module here, these are. Can you see my? For some reason, it's not appearing on the YouTube yet. You'll see it in a minute. So it will. Yeah, it will appear. So these are the three books I recommend. Fluid Mechanics by Kundu and Cohen, I wish. Physics of Fluids and Plasmas by Arnab Rai-Choudhury, and right. And the classic book on fluid mechanics by Landau and Lifshitz. There's also an unofficial set of lectures kind of a book by Gene Eilek, but it's strictly unofficial, so I would rather not. But these are books that are all of these have Indian editions, so I would yeah. Okay, very nice. So shall we? Maybe we should get started with this. Yeah. By now, I think by this point in the course, people have seen the following diagram a lot, which is that of a ball immersed in a smooth sphere, immersed in a fluid that's flowing past it, say from left to right, yeah, like that. So, say those are the streamlines of the fluid, like that. And as you go progressively farther from the ball, the curvature of the streamlines are less pronounced, and when you're very, very far, they're essentially undisturbed, as though the ball was not there. Okay, and this would be the x direction. Okay, and this is actually a cylinder, infinite in the, so this would be x and this would be y, and that would be z, and the cylinder is of infinite extent in the z direction. Okay. All right. So maybe yeah. So now I see a few other questions. Are these purely theoretical? Yash asks. Or are there problem examples? There are several problems. Look at the books. Okay. There are lots and lots of problems. Some applied, some theoretical. There's a good mix. All right. And especially for people a little more engineering oriented, I would say the book by Kundu is better. But I wouldn't strictly recommend one book very much over the other. Just take a look. Okay, there are plenty of problem examples. All right. So coming back to this, you have seen the solution. So the thing is, in this case, you completely, for this kind of a thing, if you completely neglect viscosity, if you assume a perfectly inviscid flow, then you know that you can write the velocity in terms of the gradient of a scalar potential. Okay. So what you do is yes, that's right. Yeah. So you needed to. I would, if you're looking for a recommendation, I would say buy Kundu's book. Okay, see how it feels, how it looks like. The only thing is that you won't have much about astrophysics, and you won't have much about magnetohydrodynamics. Okay, but it's a good book. And the same with Arnab Rai Chaudhury's book. It costs a few hundred rupees. Cambridge. Okay. Yeah, that's right. I believe they also have an online. Yeah. So take a look. All right. So now coming back to this problem, the solution, the solution to okay, del square phi equals 0 with appropriate boundary conditions. Boundary conditions are the main thing, right? Is in this case they are so is equal to u times, and if you want to know where this came from, it's always possible to plug it in and do all the good things. Okay, but the cheaper and easier way to do it is hold on. Yeah. So plug it in and verify. Okay, plug the solution into this, into this equation. So what you do is you simply write down the del square operator in what you call in spherical polar coordinates, and you'll find that this is a bona fide solution. In what sense is it a bona fide solution? It satisfies the right boundary conditions in that these kinds of boundary conditions, that there is infinite slip allowed here, okay, and far away as r tends to infinity, u is simply the same as ux. It satisfies these two important boundary conditions, and these are the only, this is a second order equation, so you have 2x derivatives, so you need two boundary conditions. Okay, now most of the questions, or a couple of the important questions in the discussion forum, dealt with rotation. So this is strictly irrotational, right? This is strictly irrotational. There is no scope for including rotation, right? Now, why are we even talking about this then? Why are we even talking about this in the context of rotation? Simply because, well, you have a well-known, elegant solution, if you take the gradient off, it looks nice. It looks like this, makes a lot of sense. The only problem is, of course, it doesn't stick at the surface. Okay, it doesn't stick at the surface. The only boundary condition is that u normal should be 0. It doesn't say anything about the u tangential. The u tangential can be, as if the ball was not there, it allows an infinite slip, which we know is unphysical. Okay, if you spun the ball like this, suppose this was a cricket ball, if you spin the ball like this, that in real life this ball is going to drag some of the air around with it. You know that it's going to drag the small thin boundary layer around it. And that dragging happens because of viscosity, because of viscous effects. If you completely neglect viscous effects, then the fluid simply slips past, and there's no scope for any dragging. Okay, but if you want to solve it properly, okay, if you really want to include, if you want to treat rotation correctly, you need to include viscosity. Need to include viscosity. No way out. Much more complicated problem. So is there any way that you can, address this in a cheaper manner? Do something to the solution that you already have, so that you are treating viscosity effectively. Turns out that there is such a way, and for that, what you do is you take this solution. Remember this. Maybe I'll write it down once again. All right. You take this very solution equal u sine the r plus. By the way, there are some problems with this. Okay, this does not, the presence of this r in the denominator will problems if you are worrying about a solution that's interior to the sphere, or it blows up at r equals 0. But there's just an exterior solution, don't have to worry about it. Okay, so what I'm doing now is, this is the solution without any circulation. Now I arbitrarily add one more term. Okay, this represents circulation. Okay, why is that? Because if you have circulation, you have a non-zero you have a non-zero line integral of u dot dl, and turns out that this is simply equal to k. If you carry out the u dot dl, what is u? Of course, you have to take the gradient of phi. Okay, and you can also curl of u dA. Same thing. But this is probably a somewhat more complicated way of looking at things. You can simply do a u dot dl, because the dl is easy enough. The dl is just over the sphere. The dl, the line element for dl is just this, right? So you can do the u dot dl, and you can confirm that it's exactly equal to k. So the addition of this term, the other way of looking at it is that you see this cosine theta. You go from 0 to 2 pi in theta, and this cosine theta is positive once and negative once. It completely cancels out. This is totally symmetric in theta, whereas this is not. It's not symmetric in theta. It's linear in theta. So therefore, that already gives you your first hint that this might have something to do with circulation. And sure enough, you carry out this integral, and turns out that it is exactly equal to k, and it has the dimensions of. I urge you to verify this. K has the dimensions of centimeter squared per second, or length squared per second. Okay. You can also think of k as the dimensions of centimeter squared per second, or area times this, where this is the rotation rate. Okay, radians per second. If you are wondering where I'm going with this, just bear with me for a minute, and I will tell you. Okay, and if you okay, Shakti Rao, I'm not sure I understand your question, Shakti. Okay, bear with me for a minute, and I will let's go over this example completely, and then I'll come to you. All right. Now you can from you can write down UR and U theta. Okay, so it turns out that the UR, if you carry out the integrations properly, it's a square over, where a is the radius of the ball. It's this, and U theta is minus U 1 plus a squared or r squared sine theta plus the all important k. Okay, this represents the effect of rotation. Okay, now what about this? Right, why is all this? And you can check that the behavior of the velocities is okay, as in it reduces to an purely x-directed flow far away. So all that, it satisfies the correct boundary conditions. Now the thing is, the reason we incorporated the rotation in here is so that we could explain lift. The point is, if you see a rotating ball, if you have a ball and you rotate it, okay, it rotates this way, it will feel a lift, either a lift in the in an upward direction or in the downward direction. That depends. Okay, but either way, there's I mean, it's being rotated along this, and it has a lift. Okay, and the whole point is this rotation breaks the symmetry. You see, the flow was nice, and it's as though the flow was nice and symmetric. Like this. Okay. Now, when you add another streamline like this here, by hand, I add another streamline like this, then what happens is the density of streamlines here is increased, the density of streamlines here is decreased. It's as if the streamlines are a little sparser here, and it becomes a little denser here, simply because this is in the same direction as this, and this is in the opposite direction as this. Okay, and what happens when the density of streamlines is, I mean, what does this denote rather? Which means that the speed here, the speed of flow here is larger than the speed of flow here. Okay, and from Bernoulli, the Bernoulli constant is half u squared plus p over rho, roughly speaking, neglecting gravity. So if this has to be constant over anything like this, when the speed increases, pressure decreases. When the speed decreases, pressure increases. Speed is decreasing here, therefore there's greater pressure here, and there's lesser pressure here. So which way will the lift be? The lift will be upwards. So we are essentially, and you can do this rigorously, you can actually figure out the lift, okay, as you can actually compute this. P, well, the pressure is this is A theta and A sine theta. What am I really doing here? I'm doing an area integral. This is the lift, and the P you find from the Bernoulli equation. Okay, you can actually compute the lift, and when you do the calculation fully, it turns out to be rho UK, where rho is just the density of the fluid, U is just the velocity of the fluid at large distances, and K is that thing. So this is how adding a term that looks like this K, okay, gives you in a way a cheap way of figuring out lift, okay, without going through all the trouble of including viscosity and actually solving the full Navier-Stokes equation. I thought this was one thing that many people were asking, and so I thought I would spend a little bit of time on this. So now, Shaktirao, can you tell me a little more? What do you mean by background fluid? How it moves when the source is moving to the left? You see, the best way to think about sound is well, I mean, here's a source, okay, and it's emitting sound waves. And if the source is moving, so the sound waves are moving at a speed given by C sub s, okay. And if you are a observer standing here, okay, and if you observe the source moving, with u, as far as if the source is moving with the speed u, then as far as the lab observer is concerned, the total speed is simply u plus cs, just a Galilean, you can exceed the speed of sound. Okay, it's allowed, unlike the speed of light. Okay, so I don't know if this is the question you're asking, or if you're asking a question related to why don't I, yeah, or if you're asking a question related to,
open the notes.
yeah, I think,
Moving source.
yeah, I think, yeah,
The directions are reversed.
yeah. You're probably asking a question about this. So which way is the source moving now?
So source is moving towards left here.
Yeah.
But the directions are.
Yeah. No, that this is okay.
Yeah.
So here the source. I think this is the question you're asking, if I'm not mistaken. And these are all iso pressure or density contours. Okay, so the source is moving to the left, and what you're okay. So the contours are squished in the direction of motion. So if you're being misled, all this is doing is that, I mean, the resultant vector is this. You're simply adding up the source velocity and the velocity of sound. Okay, so if you're confused about it, please look up the errata, and this is okay. The problem really comes when the problem really arises when the when the source is moving faster than the speed of sound, as here, and then what happens is these iso contours start intersecting each other, and that makes no sense, right? The iso pressure or iso density, the whole point of iso means it's the pressure is constant all along here. So what's the pressure here, for instance? Is it this value or this value? So that hints at the fact that there is a problem. There can be a discontinuity, and as we've seen later on, the discontinuity. These discontinuities, shocks are one kind of discontinuity. I don't know if this answered your question, but I'll tell you one thing. If this confuses you, let it be. This was just one way of explaining. Okay, you can rest assured with the fact that you're allowed to make just simple Galilean transformations, as in you can climb into the frame of the source, okay, and then the speed of sound is, I mean, the source is always emitting waves at the speed of sound, no question about it. Now, if you climb out of the frame of the moving source, in other words, if you climb into the lab frame, okay, then you're allowed to simply add the two velocities, add or subtract as the case might be. Okay, you're simply allowed to just simply add the two velocities. Okay, and that's why that explains the Doppler effect also. The fact that for a given frequency, when the source is moving towards you, it has lesser time to reach you, and that's why the frequency is apparently increased. Okay, so this is a straightforward Galilean transformation, no special relativity. There is no there's no requirement that the total speed always cannot exceed the speed of sound. No, with regard to the speed of sound, the total speed can actually exceed the speed of sound, and that leads to issues. Okay, that leads to issues with regard to supersonic flow, as we've discussed in the course. So if this diagram, if these two diagrams confuse you, never mind, just let it be. Okay, you can always climb into the into the frame of the moving source and climb out of it, and the transformation is just a simple Galilean one. You're allowed to happily add and subtract. Okay. Any other questions? I thought I would go on to another problem if there are no. All right. Okay. So y equals v is here, right? And you have the fluid is flowing under the influence of a pressure gradient. So you have a constant pressure gradient, dp dx, and that's why the fluid is flowing. I'm really sorry I scrolled so much, and there's a substantial lag on the YouTube channel. You cannot see my blackboard at all. Is there any way of remedying this? Is there any way of making sure that you can see what I'm showing right now? Otherwise, it makes no sense. Let me wait until the blackboard shows up. I think I scrolled through a whole bunch of things, and that's sort of.
It's things like that. So, both go. If you're thinking this is your voice and it's lagging, no,
not the voice. I mean, what I'm showing right now on the blackboard is not showing up there. So what I'm talking is not.
No, it will go with that. So if you're thinking that they're saying this and you're
I'm talking here
and talking,
it's not like that.
Not like that. So whatever you're scribbling here, that will only.
I see. Okay. Very nice.
You don't have to worry about this.
I see. Okay. Great. So now you see. So the question now is how does Vx behave as a function of y? This is the question. Okay. Now, this is a viscous fluid. Okay. So you would expect sticking here. The fluid would stick here and here. So you would expect the velocity, the x-directed velocity, to go to 0 here. Okay. And by symmetry, you would think that the x-directed velocity would be maximum here. Right in the middle of the channel, it would be maximum. And here, it actually goes to 0. So you would probably think, and you'd be right, I mean, intuitively, you would think that the velocity vectors would look somewhat like this. It would be maximum here. It would be, as you go through towards the wall, it would get smaller and smaller and smaller. Okay, I'm exaggerating here, until it actually goes to 0 here. I see. So what should I do now? I should stop sharing and start sharing again. All right. I should present now, and let me show my window. Okay. I started it again. It's loading. Okay, I cannot see it on there. So maybe I should. Yeah, it'll take a little bit of time. Oh yeah, great, wonderful. So let me repeat. So the question is, the statement of the problem is as follows. You have two plates, like that and like that, okay? Two plates which are separated by a distance 2b in the y direction. So this would be the x direction, and this would be the y direction. And the plates are infinite in the x direction as well as in the z direction, in the direction, perpendicular to the plane of the screen. Now, and the fluid is viscous. So now so the last example we talked about dealt with an viscid fluid where you were able to solve for the velocity potential. Here you're doing viscosity, so you will have to solve for you will have to take recourse to the the Navier-Stokes equation. Okay, but a simple version thereof. We'll see how it goes. Okay. And the fluid is flowing under the influence of, why is the fluid flowing? Well, there's a pressure difference. Okay, there's a pressure P1 here and the pressure P2 here, for instance. Okay, this is just for sake of illustration. And if P1 is greater than P2, in other words, if there's a non-zero dP dx, the fluid will flow from left to right. All right, now the question is, what is the question we are asking now? Both these places are stationary. Let's just keep it that way, and let us see how it goes. Okay. Now the question we want to ask is, so fluid, there's only an x component of the fluid flow. All right, and you want to ask, how does the x-directed velocity behave as a function of y? This is the question you're asking. Okay, and intuitively, you would expect that the x-directed velocity would be maximum at the center at y equals b, yeah. And by the time it reaches the walls, because the fluid is sticking, you would expect, this is viscous, say, I think motor oil or honey or something like that. It sticks to the wall, so the fluid essentially comes to a stop right at the wall. And in between here and here, there would be some kind of gradation. The velocity is maximum here, and it's somewhat lesser here, and so on and so forth. The question is, what is the shape? Okay, is it a parabola? Is it a Gaussian? Is it what? There are several such shapes that can, and it's the same here. That's the question, right? So, there are essentially, this is F equals ma, and this is steady state. So if you look at the Navier-Stokes equation, the d over dt term, it's a steady state. There's no d over dt term. So it's simply the dp dx balancing the viscous term. And this is just a constant. The dp dx is simply a constant. So it's as though you have an equation where mu d square u dx square. Okay, I should say d square. I'm confusing notation. So sorry, and this is not dx square either. I'm making lots of mistakes today. Sorry. D square. There's only one component of dy square. Vx is a function of y, right? So that's why you have a, let me write this afresh on the next one. So, which is a constant, is equal to mu, and I don't need to write partials anyway. So this is really it really should be mu over rho. Okay. So there's a flow only along x, and the Vx is a function of y. The question is, what function of y is this? Okay. Now the solution to this, if you integrate this twice, Okay, the general solution is equals some constant k1 this is the general solution. In fact, so and you plug this in. Plug in and verify. So I've already incorporated the boundary conditions here. Effect of temperature on viscosity. Okay. I will come to your question, Yash. Okay. Hold on a minute. I'll come to your question. It's not an easy question to answer. Okay. So now I've already incorporated the boundary conditions here, and the boundary conditions are Vx equals 0 at y equals 0 and y equals 2b. In other words, at the walls. At the walls, y equals 2b and y equals 0. At both these places, the x-directed velocity comes to 0, and you can verify that this satisfies that. Okay, and so what will happen is I mean, if you plug this in here, you'll find that the k1 is essentially becomes rho over 2 mu dp dx. Okay, so there's only one constant of integration, and that constant is determined like this. If you just plug this in, so what does this look like? This looks like a parabola. So that's the answer to our question here. We were asking, so what does this look like? It looks like if you join the tips of the velocity vectors like this. I'm not drawing it very well, but this is essentially a parabola. Now you can make this question, you can make this problem a little more interesting. You can say, you can ask, what if? So you can ask, what if the upper plate? What if the lower plate remains stationary but the upper plate moved in the x direction, of course. Okay, the upper plate moved in x direction with speed u. Okay, so now what will happen is the solution now would be the y. I mean, you have the x momentum equation. You have two equations. Okay, one would be the equation that you've already seen, and there you would also have to you would also have to consider momentum equation in y direction. And then what happens is the solution, the Vx, becomes some constant a times y plus b. So what happens is now instead of looking parabolic, it becomes linear in y. Okay, so the fluid would look like, so this fellow is moving like that, and this guy is stationary. So since it's linear in y, the x directed and it's sticking here. Okay, so and it's actually the fluid is also sticking to the upper plate, but the upper plate is moving with the velocity u. So the fluid here is also forced to move with the same velocity. So the velocity vectors would look something like this. Onto it moves exactly with the velocity u. So if you join the tips like this is some kind of ay plus b, and you choose the a and b constants so that you match the velocity u here at y equals 2b, and you match the velocity 0 at y equals 0. So this is an interesting variant of the problem. Okay, you can also think of two concentric cylinders. Okay, you can think of a viscous fluid between two concentric cylinders. This is the, this is what you would find, like that. Okay, and maybe the outer cylinder moving or the inner cylinder moving meaning rotating. Okay, same principle. It's just that you would have to write down the Bernoulli, the Navier-Stokes equation in cylindrical coordinates. That's all. Same principle. Either way, if it's viscous, then it has to, obey the boundary condition. If the outer cylinder is moving, then it had better rotate along with the outer cylinder with the same speed as that of the outer cylinder when it's here. And if this is stationary, it had better come to a crashing halt here. Okay, so it's the same principle. All right. So now Yash has asked effect of temperature on viscosity. Effect of temperature on viscosity is not included in the Bernoulli constant. No. Okay. If viscosity is a function of temperature, okay, you need to specify that, and that complicates things. But no, I mean it's not included in the Bernoulli constant. The Bernoulli constant is just a statement of energy conservation. Okay, it says that the specific energy is conserved. That's all the Bernoulli constant is saying. Shakti has asked my research about coronal mass ejection. You can look up my webpage, Shakti. My webpage is. I believe this is also somewhere on the NPTEL side, but Yash, I'm not sure what you're saying. You meant pressure. What does velocity potential phi mean in theory? The velocity potential simply means that you're allowed to write the velocity as the gradient of a scalar potential. The only time you can do this only if curl of u 0, because curl of the gradient of any scalar, this is always 0. Okay, so you can write, you can express velocity in terms of a scalar potential only for irrotational flows. and not otherwise. Okay. So Yash is saying pressure is an NKT. Okay. Right. So, oh, okay. You see, pressure P equals NKT says nothing about viscosity. There's no viscosity here. Okay, viscosity can, well, you see, I mean, you've seen these advertisements, right? For motor oil. Motor oil, it retains its viscosity even under high temperatures, even when the engine is heated. Okay, so I thought that was the kind of, I mean, so viscosity in real life, viscosity is indeed a function of temperature. Okay, viscosity is indeed a function of temperature, and it can often be a fairly complicated function of temperature. But that is not something, I mean, that has to be independently prescribed. As in, you measure viscosity. Sometimes the fluid thins. Okay, the viscosity decreases, and you've got to keep it within acceptable limits. All right, and yeah, so the fact that viscosity is a function of temperature does, since P equals let me yeah, since P equals N kBT, as you've said, and so so you can see if viscosity is a function of temperature, you can also equivalently write viscosity as a function of pressure. That's fine. Okay, that's what you're implying. That is fine. But the thing is, the Bernoulli constant makes no mention of the viscosity. Bernoulli constant is just P over rho. There is no viscosity here. It's the Bernoulli constant. Okay, so yeah, so that is, yeah. So any further questions in the last 5 to 6 minutes that we have? Shakti, yeah, undisturbed velocity, I mean, an undisturbed flow can affect a spinning body. You either spin the body or you spin the flow. It's equivalent. As in, I'm not sure what you're asking. You set a body spinning. It's the yeah, right. You set a body spinning and the flow is disturbed only close to the body. Far away from the body, the flow is undisturbed. Okay, you spin a cricket ball, the air close to the cricket ball does get dragged with the ball. But that is because of the effect of viscosity, which is why the air is sticking to the ball, and the fact that the ball is spinning, it drags that small boundary layer along with it. But you see, viscosity is a complicated thing. You have to solve the Navier-Stokes equation. It's a big headache. What we did here was we used the relatively well-known, fairly simple equations describing velocity potential, and by hand we included rotation by hand. We included the circulation by hand. Okay, this is not quote unquote real, but it gives us the advantage that including the circulation allows us to understand how lift is produced. And if you carry out this calculation, you'll find out that the lift is directly proportional to this circulation constant. Okay, so I'm not sure I completely understand your question. I mean, as in the velocity is indeed undisturbed, far away from the body. Close to the body, the velocity field will be disturbed. And by artificially including a circulation in an inviscid solution, we are, in some sense, simulating the effect of spinning. We are artificially including this kind of a circulation, and by doing so, we are making the flow lines, the stream lines, more closely packed on the top and more loosely packed at the bottom. As a result, the pressure at the bottom is larger than the pressure at the top, and therefore there will be lift in the upward direction. Will we be studying about temperature effects in the course? No, Yash. This is really not. Yeah. Far away from the body? No. So Shakti, no. Far away from the body. You have a boundary layer. If you are about 10 boundary layers away from the surface of the body, no. I mean, the flow is still undisturbed. And so, Yash, no, we will not be studying about these complicated effects of, temperature-dependent viscosities and things like that. No, if that's what you're asking. You see, astrophysics. I mean, yeah, we deal with very broad brush descriptions in astrophysics. Okay. Any other pressing questions? I wonder if anyone else is there. I mean, there are two people asking questions, which is very good. Like it if someone else also asked. And I apologize for the drilling, if you can hear it. You cannot? It's cancelled. Cancelled. Ah, okay. Okay. All right. Okay. Very nice. So I just wanted to solve a couple of representative problems and answer any other questions that you might have. Please feel free to keep asking questions on the plasma in this course. Yes. Okay. See, yes and no. We will be talking about plasmas in the fluid approximation. Okay, we will be talking about plasma in the. I mean, we will be talking about magnetized fluids in this course. Okay, just hold on, and in a week or two more, we will be starting magnetohydrodynamics. Okay. Plasma per se, the plasma description, we will not be talking about in this course, but we will be talking about the fluid approximation of plasmas. Okay. So yeah. So I say it's been an hour. Will there be? Oh, definitely. Yes. I definitely hope to have more live sessions in the future. Yes. I apologize that it's taken this long to have the first live session. There are lots of things going on, and I will do my best to have more frequent live sessions. Okay. I let me look at my schedule, and I will. I will now, especially now that we've done this. It works. I know how to make it work. So we will definitely. I mean, it gives me some more confidence that we can do this live session. It's not that much of a. So I've gotten over my inertia, and yes, that absolutely. The course, the recommendation is to have one live session per month. I will try to have more than that. Okay. Feel free to ask your questions in the discussion forum, and we will do our best to clear your doubts. And so that's about it, I guess. Yeah. Thank you too for yeah. So I have turned down my camera. I don't know if you can see me. Right. Okay. So thank you all. One more question.
Oh, so refer both. So he is asking whether to refer book or the lecture.
Oh, both Shakti. If you have the uh, you have absolutely both. I mean, if you look, I mean, I'm only covering very small portions of the book. I'm whatever I think is important and everything. But you really should be looking at the book as well. What if we imagine a supersonic sound source in 3D? Yeah. So what about it? What's your question? Sound sources, supersonic source of sound, moves. It definitely moves in 3 dimensions. No problem about that. There's nothing preventing a supersonic sound source from. In real life, all velocities are 3 dimensional. If we're sticking to 1 dimensional description, it's just for simplicity of description. That's all. The the pressure isobars never intersecting. Oh, no. I mean, that was again, like I said, that's that cartoon can be generalized to 3 dimensions, no problem. And even and the conclusions that I mentioned, they hold in 3 dimensions as well. The iso pressure contours not intersecting, they do intersect when the source is 3 dimensional as well, when the source is moving supersonically. Okay, so everything that I said for the 1D, it holds for 3D as well. And the fact that these isopressure contours intersect, the 3-dimensional contours in this case, they intersect the isopressure surfaces. Okay, they intersect is indicative of a problem. And what's that problem? The problem is that there are discontinuities in the flow, and one such discontinuity is a shock. Okay. All right. Yeah. So thank you very much, and I hope to see you all and then see some more of you in the next live session. Thank you and bye. So bye, Anurag. Is that okay? Can we sign off? Yeah. Okay. Thank you very much. Yeah. And yeah. Bye.